In this video, I'm going to talk about use of the chi-square statistic as a goodness of fit test. So we want to start out by talking about what the chi-square statistic actually is. So imagine if you have a standard normal distribution. That's what this is a drawing of. Remember that in a standard normal distribution, the mean is 0 and the standard deviation is 1. So most of the values in here are between 1 and -1. Okay, so imagine you take two scores at random from this. So I'm just going to say, just randomly, I happen to draw -0.5. And randomly, I just happen to draw +1.5, right? If you take these two values and you square them and add them together, all right, and then you take all these scores and you sum the scores, or you at least form a distribution of the scores, the distributions of the scores will have a chi-square distribution. And that is what this is a drawing of here. So you may notice I have 2 here, and this is the mean of this particular chi-square distribution. So if I just were to take 2 from this, notice that I'm almost always going to get scores between 1 and -1. So frequently when I add them together, add the squares of those numbers together, I'm going to get something close to 2. And that's why the average is 2. Rarely we'll get values that are much greater than 1 and much less than 1. So that doesn't happen very often. All right? So again, how do we get this distribution? So we took two values from a standard normal distribution, we squared them, and we added them together. And what this distribution is, this is the distribution of the sums of those squared values. Now another thing the squaring does, it removes the sign, so it gets rid of any negative values. Okay, so how about this? Now this is a null hypothesis, so that's the chi-square distribution for just taking two scores. Now you could make a chi-square distribution based on 3 scores or 4. Again, you would generate it the same way. And the more of these scores you take, it changes from a skewed distribution to something that's a little more normally distributed. So if you were taking something like, I don't know, 20 or 30 scores, we would definitely have a distribution that's more or less normal. All right, so let's test, okay, remember this is a null distribution. What if you wanted to know, well, what's the probability that when I just take one set of scores from here, what's the probability that I might get 4 or more? So that's pretty high. Well, Lane has provided us with a chi-square calculator, so I'm going to show you where that is located here on the board. Just give me a minute. Do a little adjusting here of the... Nope, that isn't going to work. Let's try this. Okay. There we go. That'll make it easy to see. Okay. So here's the list of Lane's calculators, and notice they have one here called the chi-square distribution. All right. So so let's say we had a score of 4. How likely is that? So I'm just going to put 4 in here. And remember, where did that 4 come from? So that would be actual data. So if I'd gone in to the standard normal distribution and I took 2 scores, how likely is it that the sum of the squares of those 2 scores would be 4? Now you want to see that that is pretty unlikely, because remember the mean of this distribution for just taking 2 scores is 2. If we were taking 3 scores, the mean would be 3. If we were taking 4 scores, the mean would be 4. You see what I mean? Degrees of freedom, that's how many scores we take from the standard normal distribution. So for this example, we're just taking 2 scores. So we'll put that in here. So what's the probability of getting a 4? Well, it's not too unlikely. it's about 15, or I'm sorry, about 14%. All right, so we'll go back over here to what I had drawn on the board, and I'm just going to raise this again because we're going to need to work on the board for a little bit here. Let me just make sure everything's in focus. All right, still in focus here. Okay, so if we had taken two scores, squared them, what I want to know is how likely is it that we would get 4? So this is actual data, and we're testing this data against that null hypothesis. All right? So you can see where 4 lands on here. Remember, the mean is the number of scores we take, which is 2. That's also the degrees of freedom. All right, so this area here, that's what we just looked up. And so we found that that was about 14%. So that's the area of that. So there's about a 14% chance of getting 4 or more. So not too unlikely. Okay. Well, this has all been very theoretical. I just wanted to use this to illustrate how a chi-square distribution is generated, what they mean. Now I want to take this distribution and apply it to something like an example that we might use for in science. Okay. So we're going to look at, first we're going to look at something called a one-way table. So I'm going to zoom in on this panel. Let me just make sure it's in focus so folks can see what we're doing here. All right, I think we'll try this. Okay. All right, so what we have here is an example from Indian corn. All right, so you probably know that, Gregor Mendel did all this research on pea plants. In our general biology labs here, we usually let students examine Indian corn because it's much easier to work with than pea plants. So, Indian corn, this is that multicolored corn, and the varieties we use, they have kernels that are either yellow or purple, and then the texture of the kernels can be different as well. So it can be smooth or it can be wrinkled. So there's like 2 different loci there. You have a color locus and you have a texture locus. And we know, that these things follow Mendelian genetics. So you may remember if you have like a dihybrid cross, so you probably did this back in genetics a long time ago. So let's say we had, a purple, so heterozygous, so it's heterozygous for both purple and yellow, and smooth and wrinkled, like both of those traits. If you had a dihybrid cross of these things, right, you would expect a 9 to 3 to 3 to 1 ratio. So what that would mean is you'd have 9/16 of the plants or the kernels would be purple and smooth. In other words, they have both the dominant traits. 3/16 would have 1 recessive trait and 1 dominant trait, and only 1/16 would have both of the recessive traits. And the corn is really interesting or useful to work with. A lot of people don't realize this, but each kernel is actually a seed of a plant. So it's kind of like in a single cob, you have all the offspring of crossing 2 plants with that genotype. So, it's sort of useful to work with. So one thing we've had students do in the past is we've had them go in and actually count the kernels and score them for each one. So what I have here is I have some actual data. So we had this student go in there, and on a cob there were like 1,000, more than 1,000 kernels. But he looked at each one, and 700 of them were purple smooth, 200 were purple wrinkled, 200 yellow smooth, and only 75 yellow wrinkled. So this is sort of the null hypothesis we're going to test. Corn traits follow Mendelian genetics. So we're expecting that ratio. That's what we're expecting to happen. The alternate would be, well, no, they don't. So if this data doesn't match that null hypothesis, then we will reject it and we'll accept this alternate hypothesis here. So what do you do? How does this relate to a chi-square? Well, what we do, this is called a one-way table. What we do is we calculate observed values and expected values. This is sort of the first step. So to get the expected values, what you do here is you add up all these observed values, right? So remember there were 1,175 kernels total. Well, if we're expecting 9 out of 16 of the total to have, the two dominant traits, then if we just take 9/16 and we multiply it times 1,175, that'll give us the expected values. Okay, so the next step is you do that with each one of these, and if you were to sum those, it's going to give you the same amount because those are all fractions or sixteenths of that total. So that's a good way to double check your math. So at that point, we'll have what has been observed, and then we also have what we're expecting to happen under Mendelian genetics. Okay, so how do we get a chi-square? Well, let's take a look at this panel over here. This will show what we're going to do next. And I'm going to move over to Excel in a minute because trying to do all this by hand can get really tedious. All right, this is the value that's going to give us a chi-square statistic, or the formula that's going to give us a chi-square statistic. So notice what we're going to do. We're going to sort of find the deviations between our expected values and observed values, and we're going to square all those deviations, and we're going to add them all together and divide by the expected value. So for each one, actually, hold on, I've written this incorrectly. This should be like this. In other words, you do that for each value, each expected value, and then you add them all together. All right? And got to be careful when you're doing this. Remember, you want to square the deviations and divide by the expected score. Don't, find out what the deviations are, divide the expected score, and then square all that. Don't do it that way. All right, this is going to give us a chi-square value. So I did this in Excel because nobody wants to try and do all that by hand. So we'll go back over here. Let me show you one other thing, and then we'll go back over here to the computer to see how we get these chi-square values and probabilities. For this one, because we're sort of working with data, we actually lose a degree of freedom. All right. So the way we find the degrees of freedom for this particular statistic is we take our number of groups minus 1. So there's 4 groups here, right? We have purple smooth, purple wrinkled, yellow smooth, yellow wrinkled. That's 4 groups, and that gives us 3. All right. So again, we're going to look at our observed values and our expected values, which we would calculate separately, and then find the deviations to calculate the chi-square statistic. All right. So we'll come back over here. I'll show you how we do this in Excel. Again, it's a handy way to save some time. All right. Let's see if I can get this a little bit higher here. Nope, that's as high as it's going to go. Great. Okay. Let me see what we can do here. Hold on just a minute. Okay, that's what needs to happen. Hold on. Oh, Lord. Let's try this. Yeah, we're going to be doing everything else in this on this computer, so we're going to need to see the screen clearly. Okay. Oh, still right. Maybe about there. Okay. All right. Okay, so first we'll take a look at the Excel file here. All right. So this is the example that I had on the board there. All right. Let's see if we can get in a little closer here. We can see this clearly, hopefully. Oh, mercy. There we go. Okay, so let's see. So what I did is I just set up formulas here. So I took the difference between the observed and expected, right? And I squared it. I don't know of a way to make this square thing, so I just multiplied the two together and then divided it by the expected values. So here are the expected values calculated the same way I calculated them on the board. These are, the deviations divided by the expected scores, and then there's the total. So I'll put this whole spreadsheet on D2L so you guys can look at it separately if you want to see exactly how I got these formulas. Then I just had it figure out what the sum is. The sum of these deviations divided by expected values is equal to 6.087. Okay, so that's the chi-square statistic there. All right. Now what we do to get the probability is we just hit Control Copy so we don't have a rounding error. And then we go to Lane's chi-square calculator. All right. Okay, and we'll put that in here. All right. Now remember we had 4 groups total, so that is each of the combinations of traits. We lose 1 degree of freedom, so you need 3 degrees of freedom here. Hit calculate, there's the probability. So how do we interpret that? Well, it's greater than 5%. What that means is we can't reject the null hypothesis. But we got to also be careful not to accept the null hypothesis. So we need to be a little careful about how we report this. All right, so I've written that on the board over here of how to report this. So remember, the null hypothesis was that the corn is following Mendelian genetics. Since we can't reject the null hypothesis, but you can't just say the corn is following Mendelian genetics because we cannot prove that. You cannot prove the null hypothesis. All we can do is maybe we can reject it if our data is really crazy. In this case, it's not. So you would say something like, we did not find a deviation between the data and the counts predicted by Mendelian genetics, and then you put the chi-square statistic and the probability in parentheses. This time I put degrees of freedom as a subscript. Again, this is the sort of thing that you would have to tell people, what does your subscript mean? Okay? So in this case, we did not reject the null hypothesis. Now in the PowerPoint, I have this same example or something similar to it, but there I get a significant result. So if you get a significant result, like if the probability is really, really low, then you would say something like, the data, let's see, our counts do not match the predictions of Mendelian genetics. Something like that, because we are accepting the alternative hypothesis. Okay, so another application would be something called a contingency table. So we're going to do this in Excel because it requires a lot of calculating and a big table and all this kind of stuff. So we're going to see if we can't let you guys look at it in here instead. It'd be a little easier to follow, I think. Okay, let's see here. See if we can get this. There we go. Okay. right, so I'm going to put this away for a little bit. All right, so this is my contingency table example. So what we have here, this is a null hypothesis we're going to look at. So we have boys or students, from 3 different grades: kindergarten, first grade, and second grade. And we're going to just sort of see what kind of toys they play with, you know. So let's assume that they have the same preferences for toys. They're just as likely to pick up a truck as a car as an airplane. Okay. The alternate would be they have different preferences. So one or more of these groups is not going to do what the other ones are doing. You know, there's some sort of difference. So what do we do with this type of data? So here's so we'd run an experiment, obviously, and here's some actual data. All right. So what do we got? So this is what we observed. So we observed in the kindergartners, 20 of them, of our kindergarten students, are playing with trucks, 10 are playing with cars, and 30 are playing with planes. So it looks like they kind of like the planes. And then we have different numbers of these other groups. Notice for the second graders, we really got a lot of students. So a lot more data for the second graders than the other 2 classes. Okay. Well, that's the data, but how do you get expected values? And that's kind of the tricky thing about doing this. Other than that, we still use the same relationship. So we're going to be looking at difference between observed and expected values. We're going to square those values and divide by an expected value. So it's kind of like the same thing we did with the one-way table. However, finding the expected value is a little more complicated. So let's look over here at how we find those expected values. So that's in the second part of this spreadsheet over here. All right. So the first step would be to copy the data again, and then we need to add some new columns, like we need totals. So what these are, this is like the total number of students. See, it's 20 plus 10 plus 30. Ignore the expected for a minute. All right, and then here we have the first grade. 7 plus 5 plus 17, 29. All right, notice as far as the second graders go, we have 188 of those folks. All right, so there's 277 students total. All right, now out of those 277 students, if we sum all of the ones playing with trucks, 83 of them are playing with trucks. See that? And then we do the same thing for cars and planes. Okay, so how do we get the expected value, this value here for the kindergartners? How many do we expect, assuming that they all have equal preferences? If that's the case, how many do we expect to be playing with trucks? Okay, so how you do it is you look at it like this. So you see how there's 60 of them total, right? There's only 60 kindergartners. But we're expecting out of all the students, 83 of them, and so 83 out of 277, you see, are playing with trucks. You see that? But there's only 60 kindergartners. Now, the null hypothesis is that for each one of these groups, the kindergartners, the first graders, and the second graders, they all have the same ratio. In other words, the same preferences. We're expecting 83 out of 277 to always be playing with truck. You see how that works? So now we say, all right, well, as far as the kindergartners go, there's 60 of them. So if we take 60 times that, that gives us our expected value. And then you do the same thing for the first graders. There's only 29 of them. So 29 times 83 over 277 gives us that. And then here we have 56, I'm sorry, not that one, 188. We have 188 second graders. So 188 times this fraction gives us that value. Now, we can check our math. Notice if we sum the expected values, it is the same as the observed values. Anyway,
To do this, we would do the same thing over and over for every one of the cells. All right? Then the next thing is we would need to calculate that same formula we used before. So we would take 20 minus 17.9783, square it, divide by 17.9783. We'd add that to 7 minus 8.6 blah 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 squared divided by 8.6 blah blah blah, etc. That gets to be a real pain to calculate. So the good news about this is we can take this data and put it into PAST and have PAST generate our chi-square statistic. Even though we can do that, for this class, you still need to know how to find these expected values. So you kind of have to know what's going on, in other words. So I will ask you to generate some expected values. PAST will not give you that information. What I'm not going to make you do is go through the rigmarole of adding and subtracting and dividing all this stuff up. You know, that gets to be a real pain. One other thing we need to talk about before we go to PAST, what are the degrees of freedom this time? So the degrees of freedom for a contingency table like this, it's the number of rows minus 1 times the number of columns minus 1. So for this data, we have 3 columns and 3 rows, right? Kindergarten, first and second, truck, car, plane. So it would be 3 minus 1 times 3 minus 1 equals 4. That's the degrees of freedom. You have to be able to calculate that as well. Okay, now let's look at PAST. So to work with PAST, what I did is I just copied this data. I didn't even bother to keep the labels. You don't really need that. So here we have the data. Now let me just make sure this is clear. Alright, I think if I lower this whole thing, it'll be a little easier to see there. Alright, let's see. Okay. So what I've done is I've put the data into this, and then I've selected the 2 columns, the 3 columns. So here's the data that we had. Notice you don't put totals. You don't put expected values, you just put the raw data. So you select the 3 columns, and then you go up here to univariate. All right, see it says contingency table. Select that. You'll always get some little error message, just hit this. All right. Okay, so what this has generated here is it has generated a chi-square statistic, 18.15. Notice it tells us the number of columns and rows. It tells us the degrees of freedom, and it gives us a probability. This time, notice the probability is pretty low, really low. It is less than 5%. So we're going to reject the null hypothesis, all right? Okay. So how would we report that result? All right, I'm going to move over here, and I'm just going to type out a conclusion. So what I would say then would be something like let's see, conclusion. Okay. Students in the different grades have different preferences. Now notice you can't really say much about who does what. Now we could go in there and we could compare expecteds to observes and try and figure out where the differences lie. I mean, with this first column we did here, you can see a lot of these scores are pretty close to one another, so that may not tell us a whole lot. It looks like these two are a little bit over and that one's a little under. But you know, you could kind of look at each set of these and see if there's a major deviation.